Okay, so hello everyone. In this video, I wanted to make an introduction into how you can compute the Thevenin and Norton equivalence of an AC circuit. So in this example, we were analyzing this particular circuit in which we have here a voltage source, we have here an inductor with this impedance, okay? We have here a capacitor, and we have another resistance. And the problem is asking us to compute the Thevenin equivalent by according to these two terminals, A and B. So basically, we want to know what is the Thevenin equivalent if we analyze the circuit from this point of view, okay? From the point of view of the terminals A and B. So in order to compute the Thevenin and Norton equivalents, well, we need to first compute what is the equivalent impedance across these two terminals. And also we need to compute the voltage, okay, as that is seen by analyzing the voltage between terminal A and B, okay? So one way to do that is to first analyze the circuit and compute first the voltage that is seen across terminal A and B, and then we can compute the equivalent impedance. And with the Thevenin equivalence, we can also obtain the Norton equivalent that consists of a current source in parallel with the equivalent impedance of the circuit across these two terminals. So first, I think that it is useful that we define that the Thevenin equivalent, okay, Thevenin consists of a voltage source in series with the impedance, okay? This is the Thevenin equivalent, and the Norton equivalent consists of a voltage source in parallel with the impedance of the circuit, okay? So this is the Thevenin and this is the Norton equivalents, okay? So for this circuit, we can first convert or compute, sorry, the Thevenin equivalent across these terminals A and B, and then we can obtain the Norton equivalents. Okay, so how can we compute the voltage that is seen in terminals A and B, okay, across these two terminals? Well, one way to do that is to apply the Kirchhoff voltage law. Okay, so we can say that we have a current that is provided by the voltage source, okay, that is, I will label this as I. And this current I is flowing from the voltage source to this inductor. But you can notice that there will be no current flow through this direction, okay? We will have 0 amperes in this direction. And the reason for that is that we have an open circuit between terminals A and B, okay? And so we can say it based on this, on this circuit, that since there will be no voltage drop across this 10 ohm resistor because there is no current flow, the voltage that will be seen between terminals A and B should be equal to the voltage of the inductor, sorry, of the capacitor, okay? Why is that? Because since we have an open circuit in this direction, there is no current flow, okay? Or there is no current flowing through this branch, okay? So at the end, the voltage that is seen by these terminals A and B should be equal to the voltage of the capacitor, okay? So we need to compute this voltage of the capacitor, and we can say that the voltage of this capacitor is equal to the impedance of the capacitor, that is minus J 10 ohms, times the current, okay? So the current is the same current that is flowing from the voltage source to the inductor, and then it goes to the capacitor, okay? Because there is no current flow in this direction. So the current that is moving from this voltage source to the inductor is going into this direction, no, of the capacitor, because there is no current flow in this in the direction of the 10 ohm resistor because we have an open circuit. And this is the Thevenin equivalent. if we analyze the circuit from these terminals A and B. Okay, so we can say that this is equal to the Thevenin voltage. Okay, I am labeling this as VTH. Okay, now we can apply now the Kirchhoff, okay, the Kirchhoff voltage law to this loop. Okay, so we can say that the Kirchhoff voltage law is minus 50 with an angle of 30 degrees volts plus we have the voltage drop in the inductor, that is J times 20 ohms times the current I, plus the voltage drop in the capacitor, okay? That is minus J 10 ohms, okay? And this is multiplied by the current I. And this should be equal to 0 because we're applying the Kirchhoff voltage law to this loop, okay? To this particular loop. Okay, so we can compute the current. The current should be equal to 5 with an angle of minus 60 degrees amperes. Okay, and now with this current, that is the current that is flowing, okay, this current is also flowing through this capacitor, well, we can compute the voltage, okay, of this inductor, that is the voltage of the voltage of this capacitor. Okay, so we can say that the voltage of this capacitor is equal to the voltage between terminals A and B, that is equal to the voltage, the Thevenin voltage. Okay, and the voltage of the capacitor is equal to the current I times the impedance of the capacitor, that is J times 10 ohms. Okay, and this is equal to 5 with an angle of minus 60 degrees. Sorry, this is equal to, yes, 5. And this is equal to, okay. Well, we need to substitute I in this part, and we multiply these two terms together, and we will have the following result, that is 50 with an angle of minus 150 degrees, and these are volts. Okay, so that is the result for computing the voltage across terminal A and B, that is the Thevenin voltage. And now we need to compute the equivalent impedance. So to compute the Thevenin the equivalent impedance, okay, across these two terminals A and B, we need to assume that all of the sources are turned off. Okay, so to do that, well, we can turn off this voltage source, okay, and then compute the equivalent impedance across these two terminals. So we need to redraw the circuit again. So remember that when you turn off a voltage source, you can represent that as a cable. Okay, so we can have the following circuit. We have here a cable, then we have here um, the impedance of the inductor, that is J times 20 ohms. Then we have here this branch that has a capacitor, okay? That is, the impedance of this is minus J 10 ohms. And we have here the resistance of 10 ohms, okay? And here we have terminal A, and here we have terminal B, okay? And you can observe that, well, if you look closely into this circuit, and we need to compute the equivalent impedance between terminals A and B, no, we're going to compute a CTH, okay, that is the equivalent impedance between these two terminals. Well, we can simplify the circuit as follows. First, you can notice that we have this inductor and this capacitor in parallel because they are sharing two nodes. And we can also observe that the equivalent impedance of the parallel between the impedance of the inductor and the capacitor is in series with this 10 ohm resistor. So first we can simplify these two impedances, and this will be equal to the following. So we have the parallel between J times um, 20 ohms that is in parallel with minus J 10 ohms. And this is equal to um, minus, uh, minus 20, okay, J ohms, okay? So let me verify that, just 1 minute. I want to be sure that I am computing correctly this impedance. And this will be equal, okay, it is okay. We have this impedance. And well, we have the equivalent circuit that we have here the equivalent impedance between the parallel between these two elements. Here we have the 10 ohm resistor. The impedance of this element is minus 20 J ohms. And here we have the terminals A and B. And we can say that the equivalent impedance, okay, is equal to minus 20 J ohms plus 10 ohms, okay? And well, this is the Thevenin impedance, okay? So, well, we can say that the Thevenin equivalent of this circuit is, here we have the voltage source that is equal to the Thevenin voltage that is in series, okay, with the equivalent impedance. And well, we have the circuit, no? And remember that the Thevenin voltage, okay, and according to our previous result, is equal to a 50 with an angle of minus 150 degrees volts. Okay, and the equivalent impedance is equal to minus 20 J ohms plus 10 ohms. Okay, now we can also compute the Norton equivalent. The Norton equivalent, okay, is as follows. We need a current source, okay, and we need in parallel an impedance, okay, and we name this impedance as Cn, okay, but the Thevenin impedance, okay, and the Norton impedance are the same. Okay, so we can say that the Norton impedance is equal to the Thevenin impedance, okay, that is equal to minus 20 J ohms plus 10 ohms, okay? And mm, the Norton current source, okay, the Norton current source is equal to the Thevenin voltage divided by the Norton impedance, okay? So the Thevenin voltage is 50 with an angle of minus 150 degrees volts. And this is divided by the Thevenin impedance or the Norton impedance, that is 10 ohms minus 20 J ohms. And this is equal to, just one moment. This is equal to, um, okay, this is equal to 2.23 60 68 with an angle of minus 86.56 50 degrees, and these are amperes. Okay, and that's it. No, we have now computed both. These are the Thevenin and Norton equivalents. Okay, so basically, remember, no, the Thevenin equivalent is a voltage source in series with an impedance, and the Norton equivalent is essentially a current source in parallel with an impedance. Okay, both impedance of the Norton and Thevenin equivalents are the same, and we can compute the Norton equivalence by using the Thevenin voltage divided by by the Thevenin or Norton impedances. Okay, so this is one brief example of how you can compute the Thevenin and Norton equivalence. I hope it is useful for you, and see you later.